Welcome to this explainer. Today, we're going to decode the notoriously dense engineering standard known as API 650. We'll be taking all that complex math and transforming it into a practical, step-by-step roadmap for designing a massive, structurally sound oil storage vessel. Let's get right into it. So here is our roadmap for the design process. We'll start with the API 650 basics, move on to materials and corrosion allowances, and then tackle designing the tank shell itself. After that, we'll look at roofs, openings, and connections, followed by fabrication and welding rolls. Finally, we'll wrap up with inspection and final testing. All right, Section 1 API 650 Basics. Let's establish exactly what this standard actually covers before we start building anything. Think of API 650 as the ultimate structural rulebook for safe above-ground oil storage. Now, to be specific, this standard is meant for welded tanks of various sizes and capacities, but it is explicitly designed for internal pressures that do not exceed 2.5 pounds per square inch gauge. So we aren't talking about highly pressurized gas vessels here, right? We're talking about massive storage units dealing with immense hydrostatic weight from the liquid inside, but relatively low internal vapor pressure. Anchoring our mathematical design process in real-world physical space is absolutely critical. Take a look at this. Notice the clear distinction between the tank's maximum capacity and its actual net working capacity. You really have to factor in the minimum operating volume remaining at the bottom and, of course, a strict safety margin at the top. Because, overfilling one of these things, that's a literal disaster we want to prevent. Moving on to Section 2, Materials and Allowances. Now that we have our dimensions mapped out mentally, we have to talk about environmental wear and tear. Because you see, you can't just build for day one, you've got to build for decades of continuous operation. Since safety is our absolute priority, we must consider the highly reactive vapor space sitting above the liquid, plus the atmospheric environment right outside the tank. And we can't forget to add specific allowances to vulnerable spots like nozzles and manholes. Heck, even internal structural members aren't exempt from these strict corrosion allowances based on whatever reactive liquids you're storing. Our physical design begins right at the foundation. We use precise stress tables to figure out the proper thickness for the annular bottom plates. Notice how the thickness of these critical foundation plates is directly tied to the stress experienced in the very first shell course, which is just the lowest ring of the tank walls. We really have to ensure the bottom can safely handle the massive transfer of forces coming down from the towering walls above it. That brings us to Section 3, Designing the Tank Shell. This is really the core mathematical challenge of our explainer. So, to determine exactly how thick those steel plates actually need to be, engineers primarily rely on what's called the 1-foot method. These formulas calculate the minimum required shell plate thickness for both the standard design condition and the hydrostatic testing condition. The logic here is honestly pretty brilliant. It calculates the required thickness at a critical design point exactly 1 foot above the bottom of each shell course. Why? Because that represents the highest pressure area for that specific section. Rather than getting intimidated by the math, let's look at how these variables translate into tangible realities. SD represents the product design stress, basically the physical limits of our chosen steel. ST is our hydrostatic test stress, used for when we fill the tank with water to test it out. G is the design-specific gravity, which is literally how heavy the stored fluid pushing against the steel actually is. And finally, CA is that vital corrosion allowance we were just talking about. Now, while the 1-foot method is the industry standard for most tanks, it definitely has its limits. If you were designing a true behemoth, a tank larger than 61 meters or 200 feet in diameter, you've got to pivot. For vessels of that massive scale, API 650 mandates the variable design point method. This is a much more complex calculation, but it captures a far more accurate reading of the actual circumferential shell stresses across that massive expanse of the tank wall. Okay, Section 4, Roofs, Openings, and Connections. With a perfectly calculated shell, the next step is capping our vessels safely. The standard actually allows for several specialized fixed roof designs. They broadly divide into two camps: roofs that require internal structural support, like a supported cone resting on girders or columns, versus self-supporting domes and cones that rely entirely on their geometry, resting solely on the tank's outer shell. Your choice here heavily influences the internal complexity of your entire tank. But let's say you opt for a self-supporting cone roof. Well, you can't just slap some steel on top and call it a day. You have to apply some pretty complex load combinations. The formulas you use account for balanced and unbalanced snow loads because, as you know, snow might drift heavily to one side during a storm. They also factor in the specific angle of the roof's geometry and the overarching modulus of elasticity of the steel itself.
It's a really delicate balance of handling environmental weight without relying on internal columns.
And here's something absolutely crucial. Whenever we compromise our carefully calculated shell by cutting a hole for a pipe nozzle or a manway, API 650 mandates heavy reinforcements. Without these specialized insert plates, cutting a hole could literally cause the structure to warp or rotate under the immense outward hydrostatic pressure. You've got to reinforce what you cut. All right, Section 5, Fabrication and Welding. Because a brilliant mathematical design on paper means absolutely nothing if the physical execution is flawed. Before a welder even strikes an arc, the standard enforces strict physical preparation. By plotting the tank's diameter against plate thickness, engineers determine exactly when a flat steel plate is simply too thick to bend naturally. When it reaches that threshold, it must be mechanically rolled prior to installation to ensure perfectly matched joints along the tank's curvature. Furthermore, the standard dictates some highly stringent rules for the actual welding process. For instance, with circumferential and vertical joints made of material thicker than 40 millimeters, that's about 1.5 inches, you cannot just lay down one massive weld. No way. API 650 enforces strict multi-pass welding requirements. To mitigate the risk of catastrophic underbead cracking, welders absolutely must make multiple passes and completely remove all slag before the next layer is deposited. Finally, we arrive at Section 6, Inspection and Final Testing. This is where we rigorously prove the tank is secure before a single drop of product is introduced. The crucial point here is accountability. The standard places uncompromising responsibility directly onto the manufacturer. There are zero shortcuts. No amount of prior shop inspection lets the manufacturer off the hook for replacing defective steel or repairing dangerous, substandard welds that might be discovered later out in the field. To guarantee the foundation won't experience a massive invisible leak into the soil below, testing the bottom plates follows a rigorous, non-negotiable sequence. First up, a thorough vacuum test of the weld seams. Second, a tracer gas test to detect any microscopic leaks. And third, a forensic visual walkdown by inspectors who are actively hunting for any unexpected dents, gouges, or arc strikes. The foundation must be totally flawless. To validate the integrity of the towering shell itself, we really have to look beneath the surface. Critical butt welds must undergo complete penetration testing. Inspectors rely heavily on radiographic examinations, which is essentially X-raying the welds, or advanced ultrasonic testing. These methods reveal hidden internal flaws, lack of fusion, or porosity that a simple visual inspection could literally never catch. When we look at all these incredibly detailed rules, intense math formulas, and uncompromising tests, it all really comes back to one single question. What is the true cost of structural failure? What happens to the environment, to local communities, and to human life if we get it wrong? What happens if a tank holding millions of gallons of oil simply fails? API 650 exists purely because the cost of failure in oil storage is entirely unacceptable. It's not just math, it is a mandatory blueprint for catastrophic failure prevention. So as you step into your next massive engineering project, how will you use this uncompromising standard to ensure safety remains your absolute priority? Thanks for joining me on this explainer, and I'll see you next time.